Good afternoon, everyone. Welcome to today's PHIUS webinar. I have Katrin Klingenberg here, and she will present on multifamily passive buildings, lessons learned. A quick introduction to the webinar process. We have a GoToWebinar control panel where you may ask questions as we go along, and we'll take the last 10 or 15 minutes to answer just a couple questions. And also, I just wanted to let you know that this has been approved for CPHC CEUs, and you will receive self-reporting information at the end of the event. We'll also email that to you, and it's also been approved for 1 AIA HSW credit, and we will report that to the AIA for you. Just let us know if you haven't already given us your AIA number. And that's all from me. I'd like to introduce Katrin Klingenberg.
Thank you, Katrina. Hello, everyone, to what I like to call the first installment of hopefully a few series on multifamily buildings. This presentation is talking about multifamily passive buildings lessons learned from a fairly high level perspective. I like to follow up with 2 more presentations over the next couple of months. We're working on details books and for envelope as well as mechanical systems, and we hope to be able to make that information available to you as we are working on it, and not just in its final stage. It's great information, and we're here to push the information that we have and the progress that we have made as a passive building community out to you. So glad to be here. Just to start out here real quick, you might have heard over the last couple of years that we saw a exponential growth curve develop in the certification process here at PHIUS, and much of that exponential growth is driven by multifamily projects, and we can now very firmly state that we are in this exponential growth curve and that we are sustaining it. So this is really great news. And as you can see here in the opening slide, the building typologies in the multifamily sector, they are now reaching also high-rise construction and not only low-rise and mid-rise. All right, let's jump right into the lessons learned. I'm realizing that it's not advancing. Okay, here we go. All right, very quickly, the context. You all are aware of that. The climate crisis has been always for me at the core of my motivation of pushing for building energy reduction and with it carbon emission reductions. And in this infrared image here, you can see that this is essentially how our cities look today, and even the very new buildings. This is one here, fairly new, newly constructed in Chicago. Buildings are using way too much energy, and we really need to curb those energy emissions and with it carbon emissions in the building sector. So context, before I talk about trends and lessons learned here, obviously is the changing climate, and it is happening. I believe we all agree on this, and I don't have to go into much more detail here. So buildings play a large role. 40% of carbon emissions are in the building sector, and the building codes really have to tighten, and we still have quite a ways to go until we reach our overall carbon emissions reductions targets. And you can see right here from the International Energy Conservation Code has improved since 2012, but we still have long ways to go, about 30 to 50% more in energy savings that have to be reached. One big lesson learned in our journey of guiding multifamily passive building adoption forward in the United States has been, and this is one of the reasons why it has been very successful, our partnering with the Department of Energy Zero Energy Ready Home program, as well as with the Energy Star from the Environmental Protection Agency and the Indoor Air Plus programs and Water Sense programs. Behind that partnering was not only to be able to co-promote and benefit from greater market kind of presence and visibility, but also the harmonization of the passive building standards and programs with the existing standards, industry practices, third-party verification, so on and so forth. And you can see right here that our certification is very closely related to the Energy Star and Zero Energy Ready Home programs, and we're building on it, and we have integrated those processes into our certification process, which again, then in return made it easier for institutions that wanted to incentivize and promote passive building in their region, because they now had established programs to refer to. On the way to doing that, we recalculated and calibrated our standards. 2015 PHIUS Plus was cost optimized by climate, and we used the cost structure of North America, of the North American construction market. And you can see right here that we are still right in the vicinity here. Our goal of reduction is 86% in terms of energy use for heating demand, and for cooling demand, we are still saving 46%. Cooling demand is much harder to achieve through passive measures. That's why you're seeing a much smaller number here. So long ways to go still, but the good news is we have that program now established. It's well established. We see great growth, and we have that relationship with the Department of Energy. And we're also starting to kind of look towards the 2030 challenge. You can see right here with what we're striving for in our targets, the way they are set today, we're already achieving roughly 80% of reduction targets of the 2030 challenge. And again here, so I mentioned in my opening statement here that since 2015, we have seen some indication that there was an exponential growth curve developing, but now we're really starting to see this for sure. This slide right here from the Pembina report from 2016, first third-party report on passive buildings, so people are taking notice. And in this particular one also, it's depicting the certification share of the European Passive House Institute certification, as well as PHIUS. And again here, lessons learned, the harmonization with codes and standards in the United States really has started to drive the trend since 2015 towards PHIUS Plus certification. And just looking at our numbers right now, from our database, we are way on our way. Actually, there was very good news. Our projections were already way off in 2018. In April of 2018, we had already certified and pre-certified as many projects as all of last year. So we will likely exceed what we had projected here for 2018. And you can see that these projects are going on all over the country, in Canada as well. And that there are quite a few multifamily projects, so it's kind of hard to see. The red dots are the multifamily projects. Out of the 500 plus projects in North America, about 80 are multifamily projects. And of course, that is not happening without help from jurisdictions, city governments. All of these that you can see here in the slide have helped to make that trend happen. And again, lesson learned, if you tie into existing standards and programs, these organizations have a much easier time to incentivize a new program, i.e. Zero Energy Ready Home and EPA. And further lesson learned, we can do it now after the cost calibration of the new standards. Our affordable projects are hitting very reliably now about like 0 to 2% additional cost above code building baseline. And that is excellent news because the cost kind of hurdle has been initially the biggest challenge. There are a couple other projects here. The previous one was Hillcrest in Pennsylvania, one of the first projects certified and incentivized by the Pennsylvania Housing Finance Agency. And here 2 more projects from up north, from Burlington, Vermont, and from Maine. But again, these projects are going on all over the place. These are all fully certified projects, and they come in at very good cost results now, and this is great to see. So really, it is a proposition that why would a developer not go that route at that point, getting those savings and benefits in health and at that low upfront cost. So more lessons learned here. I'm talking about, again, I said big picture lessons learned, and that means multifamily passive building design from the beginning to the end. So basically from design, from the standard setting to construction, and then through monitoring and kind of continued commissioning of the project. You know, we switched from one size fits all energy metric and passive building standard to a climate specific standard. And you can see right here the reason why. There is a multitude of climates that require very different responses to them, and including humidity, cooling dominated climates. And to design projects accurately, it is very, very crucial to have the accurate guiding metrics, because if you don't have the accurate guiding metrics, then you might be unintentionally over-insulating, over-investing in the envelope. And in a more mixed and warmer climate, actually too much insulation will hurt you on the cooling side. So really important to have these targets and standards right before we start our passive building designs. This is here basically, this slide shows the core characteristics of a passive building standard. PHIUS Plus does constrain the space conditioning first for heating and cooling. Then whole building energy is constrained by a source energy factor. And then we also have a quality assurance, air tightness criterion that is aiming at the durability of the envelope. And of course, we do all that with an eye towards zero. So our cost optimization was done with an eye towards zero. And sure enough, we have a PHIUS Plus Source Zero badge. And again, because we want to get to zero carbon, we are not having any kind of like medium, like halfway to zero source or 3/4 to zero source. Really, what we need to get to is source zero. Cost optimized here on the left, you can see the graph from the BOP model that we used to establish the standards. This is just very quickly here to show like we're setting the standards where we have the most cost optimal investment in the envelope. And on the path to zero, with taking actual cost for renewables into account. And through the process, very important, again, to have heating demand, cooling demand, the loads for heating and for cooling all vary by climate to arrive at the best possible solution for the envelope and for the interior climate of the project. And air tightness is referred to an area measurement here, 0.05 CFM per square foot envelope, because as I mentioned earlier, it's a durability criterion. And while it is also important to assess the energy efficiency of the building, but mainly it is aiming at preventing condensation in the building envelope. And then there's a source energy factor under 2015 right here. And so this is once it's all said and done, those targets. Just quick example here, annual heating demand and cooling demand in Chicago, for example. So we have 6 for heating and 3.6 for cooling, and in Olympia it would be 6 for heating and 1 for cooling. These are not drastically different. If, for example, you go to the state of New York, they have 4 different climate zones within their state, and you can see some pretty dramatic changes. More lessons learned. So as we are traveling through all different climate zones, we are employing our regular passive building principles here, nothing new. The thermal control of the envelope, air control, and radiation control. But lessons learned, and even more so important for multifamily buildings, are moisture control measures, because multifamily buildings are very highly densely populated. We have high internal moisture gains, moisture sources, moisture load that needs to be controlled. And as soon as you move further into the warmer climates, like climate zone 4 and below, you will have in a multifamily building a cooling dominated situation. So that complicates the whole building energy balance somewhat, and really demands a more dynamic tool, not only to make sure that the hygrothermal performance of the envelope that you can see in this little movie is okay and that we don't have any condensation in that wall assembly, but also we are now able in our tool to actually model more complex scenarios such as heating and cooling in combination. And for larger buildings, for multifamily projects, it is really crucial to be able to model different zones within the same whole building energy model, and also to be able to do comfort checks. Everything else stays pretty much the same here: weather data, air exchange, inner load, set points, HVAC. And there's still a fast design feedback feature in the tool, but for multifamily buildings, again, the comfort check is very crucial. And again, here, a screenshot from WFI Passive for large buildings. Next lesson learned: building typologies really matter. I already alluded to that. Big buildings are internal load driven, and that makes them generally in mixed and warmer climate zones cooling load dominated. And you can see this here in the little check marks down here. The cooling demand actually is higher than the heating demand for this rather large project in New York City. And as a very extreme example right here, the big, large project in New York City compared to a tiny Staten Island rebuild here, single story, you can see the differences in R values that it makes. The typology matters also in terms of how much insulation you need for the envelope. And that is one of the main reasons why the additional cost has come down significantly for multifamily projects, because better surface to volume ratio means less R values all around. And the R values that you're seeing for the large building here on the right-hand side, they are first sketch R values. Once it was all said and done, the R values came down even further. We're now at around like an R20 for the walls. Usually no whole slab insulation, just perimeter insulation, and R5 windows. That still holds. So because building typologies matter and size matters, and for the first PHIUS Plus 2015 standard, we based our standards all on a single family 2,000 square foot home, not because that was the standard for this typology, but because of the logic that if the smallest home, which is worst case scenario, can meet the standards, then the larger buildings are going to be able to meet those standards as well. But to be able to be more precise and to have more granular standards, we're actually under 2018, the pilot is out right now, and we're finalizing everything, planning on launching it at the conference in Boston in September to go into effect. For that one, we now have much more granular standards because building size and building typology matters for the internal loads, for the balancing of the heating and cooling. Occupancy is a big factor in the internal loads. So we had to recalibrate the standards, and we made them much more granular, much better. So we have a new calculator now that lives on our website where you can actually type in. This is just a quick example here. You can type in your floor area, 2,500 square foot home, 4 people in it. And you can see here in this particular climate zone, the heating demand is 8 and the cooling demand is 7. So they're pretty close to each other. But if you build in the same climate zone a very large building, 100,000 square foot home with multifamily project with 200 people in it, you can see how the heating demand and cooling demand flips. And that is very, very crucial to have the right guidelines here for the designer, because like just imagine we had the same targets as in the previous slide for a large multifamily building. The bucket for the heating demand would be much too large. And the cooling demand here was able to tighten as well. All right. For 2018, we're also tightening the source energy criterion, which essentially is the effective carbon emissions equivalent indicator for our standard. And if you remember from the previous slide, previously we were at 6,200. We're tightening it to 3,840. That seems like a really, really big jump per person. But we also changed the rule, and other than before, you can actually now count all renewable energy towards meeting that source energy target. And the reason for that kind of shift in thinking is that we have to get to zero eventually. And we had set it to taper to zero by 2050 initially, but the tech committee recently reconsidered and is likely going to align with 2030, with the 2030 challenge to get to zero at that time. So no longer is only the amount of energy that you produce on site countable towards meeting the source energy targets, but also the now you can count in all energy production, and also green certificates, renewable energy certificates are allowed to meet the source energy as well. Now we get into the construction lessons learned. So same happened here. We learned very quickly that climate makes a difference in choices of the components, but also the building typology yet again makes a difference in choice of components. And very obvious case was this large building that I showed you earlier in New York City. That project actually was able to reduce the R value of the window to a point where they were able to buy a very, very good double pane window and meet their energy targets. And the reason here is that, again, in a multifamily project, we have such high internal loads. And if we have a heating and cooling season, we need to balance all those loads against each other. And actually, in the summer, the slightly lesser high R value window allows for more losses and results in lower overall total cooling demand. Ventilation systems and ERV, HRV issues, heat humidity recovery versus no humidity recovery, and humidity control becomes a big issue in multifamily buildings as well, again, because there are high internal humidity loads already. So initial pre-dehumidification, but also not too high of a humidity recovery is important so that one does not inadvertently add to the problem. And then wall assemblies, they can now, because of the typology of multifamily buildings, larger units, less R value, it is much easier to realize those wall assemblies with pretty standard wall assemblies that are being used in standard construction. The additional R value that is needed to meet the targets are not very much, really. It's pretty much business as usual. So that was the big lesson learned out of all the first fully certified and occupied projects now. The project teams really worked hard to meet the budgets, and their first strategy was use what you normally do and try to solve thermal bridging detailing as well as air tightness detailing through smart design, basically. But do not change the construction so to a point where it is going to be very different. And you can see right here, this is the detail from Portland, Oregon. And they actually were able to take the hit from the foundation thermal bridge right there because the climate is fairly mild and the footing is not all the way insulated all the way around. And the only limiting factor there is, like, of course, you have to do a condensation check at that interior corner there where that thermal bridge occurs. But if that is okay and there's no condensation risk, then this detail is perfectly fine and is much easier to execute than a fully insulated complete footing. So the next project right here, project teams very quickly also ran into more elaborate wall assemblies, of course, not just like frame and exterior continuous insulation. We have here face brick and cladding systems, and then at that point, very quickly, one gets into the question of thermal bridging, attaching certain structures to the structure back. And teams had to become inventive to overcome these thermal bridges. But again, they came up with very cost-effective solutions, and I'll show you what they did here a little bit later. So air barrier, what we see generally, the teams are very, again, they follow that advice, take construction materials that are already being used on site. Here in this particular case, we have the sheathing, the structural sheathing that this project team here had to install anyway. They are adding a liquid applied air barrier system on the exterior, and then the continuous insulation layer is being applied on top of that. This seems to be a very successful strategy, easy to inspect and make sure that the air barrier is successfully applied. A lot of teams are going that route these days. This project here, Orchards at Orenco, was one of the very first projects, multifamily projects. And that team actually didn't even go to great length, and they didn't use an exterior spray applied air barrier. They basically just used the plywood sheathing and taped all the seams and used that as their air barrier, which is perfectly fine, saves additional money. Again, they applied the rule, use the business as usual construction as much as possible, and that was their strategy. And you can see the air tightness layer, and that's what I meant. In the next installment, when we talk about envelopes, we'll go into more details and look at exactly how these teams detail the air barrier, but just general lesson learned here, crucial to get everybody on board and detail that air barrier as simply and continuous as possible, not as possible, like really make people do the exercise of putting the pen on the paper and don't take it off, and think about how to construct that continuous air barrier. In this particular case, this construction team decided to change their detailing at the parapet. They did not let it go all the way up because they wanted to have the opportunity to continue the exterior plywood air barrier up to the roof and make sure that that seam is 100% foolproof, airtight. And then they decided to add the overhang parapet on top of that as a separate piece after the air barrier was completed. So very important to think through all these details, where the air barrier might get penetrated, and as soon as you can start detailing your air barrier, the better, not just like as an afterthought, then it will be the most cost effective. Now this project here, Orchards at Orenco, also a very interesting project because the first phase was still built to the European standard. You can see right here is pretty significant difference in that fairly mild climate from the PHIUS standard to the PHIUS Plus standard, 2x10 structure at the first project, and then 2x6 for the second. And I think the difference in overall site energy use consumption projected was about 5%. So clearly an example here for too much insulation really can push you back up into diminishing returns. Exterior air barrier, a couple other options here for very large buildings. We have one here on top of the gypsum. Can be equally well applied and quality assured in the city if non-combustible materials are required. On the right-hand side here, this is insulated concrete forms that have basically built-in airtight layer in the construction itself. And then also we've seen a few initial panelization approaches where the airtightness, you can see right here on the right-hand side of that panel, there's a gasket lip that is sticking out. So the airtightness detailing becomes pretty intricate in these panels, and it's not necessarily the cheapest solution. It is, in our experience, and what we've seen from the project teams, always better to go with business as usual for now until people figure out how to industrialize these panels. So continuous insulation, I mentioned the ICF as a good airtightness strategy, but of course it gives you also the continuous insulation, which makes this construction technology really, really cost effective. So if you can use multiple materials for the same purpose, or a system gives you 2 out of the crucial passive building strategies, continuous insulation and airtightness, you're already quite a ways there in meeting the targets. And this was one of the projects that also met, was constructed at, I think, like 1 to 2% additional cost. If you do just concrete frame construction, no problem, business as usual. Again, even steel studs, not a problem. Keep the insulation outboard of it though. We have thermally broken connectors for the continuous insulation, in this case here mineral wool, it really is not worth it to insulate between the steel studs, because there's a significant reduction of almost 50% just because of the loss that is caused through those steel studs. So ideally, keeping all the insulation outboard will get you the biggest bang for your buck per inch of insulation. And then here's the solution, very cheap, like a little compressed plastic disconnector behind each of those connectors for the exterior wall panel system for this project. And it's just a small little plate that decouples the steel connector from the rest of the structure of the building. And it makes a big difference in terms of cold being drawn into the wall assembly or not being drawn into the wall assembly. You can see it here up in the right-hand side. That's not a very good detail. And then multifamily projects often have are in need of solutions where the thermal envelope will have to be penetrated by structure because of a parking deck that is open to ambient. And here we also have solutions. There are plenty of manufacturers out there now that have structural thermal bridge kind of disconnectors that can be used in those situations. And then my starting slide here of the Aqua Tower in Chicago, of course, this should have been used, the decoupled kind of thermal break right here for the cantilevering balcony, and in the defense of the architect, it was actually specified, but it got value engineered out of it. That piece of equipment could have made a large difference here. Now let's get into mechanical systems. Quick overview here, this is actually a fantastic system here from, again, the Orchards at Orenco project in Portland, Oregon. That said, that is as I mentioned, a fairly mild climate. The good news about multifamily projects is that generally the peak loads are very low. And if you are in a climate that is not cooling dominated, or at least not too warm, the peak loads can actually, both for heating and for cooling, can actually match your required ventilation air. So in this particular case, that's what they did. They integrated a heat pump into the delivery system of the energy recovery ventilator. And that's, you see here in floor plan, in that sketch of the system, with a summer bypass. But if there is a need for cooling or heating, the heat pump puts that low peak load into the delivered airstream. And that is the only way how this building actually has some cooling in it. Again, in that climate, this is not a problem, and it's not a highly densely populated multifamily building. There are much denser solutions which probably would not allow this type of solution. This is an example here for the centralized solution. And one more thing. Well, there's a little centralized. There's a little bit of decentralization here as well. They have backup electrical heaters in each apartment just in case. But experience and measured data has shown that people rarely turn those on. And one more thing is worth mentioning here, and that is that the centralized solution for ventilation systems is a really good solution for low-rise multifamily projects, as you can see right here. In this particular case, they actually have a mechanical penthouse on top of 6 units, and then 1 unit serves 6 units. But as soon as the building gets taller, the stack effect starts to work against you in the ventilation delivery system. And at that point, we very strongly recommend to either do centralized for a small set of floors or do completely decentralized solutions for the ventilation system. In most cases, it's a combination of heat pump and ventilation system in the multifamily projects. And in the larger ones here, one in New York City, we see semi-decentralized solutions. So some teams have opted for ventilation systems for each apartment. Definitely if it is a condominium and the apartment owner wants to have full control over the ventilation, that is very much recommended. It is maybe easier if it is an affordable project and the owner does not want people to turn the ventilation system off, then maybe it's better to centralize it. But if it is a condo project, definitely we would recommend that there should be an individual unit in each apartment, which of course comes with some challenges. You can see right here on the right-hand side, you will have to place the intake and the exhaust in the facade, and the taller the building gets, the more difficult the maintenance becomes, and details have to be designed so that actually those grills can be maintained from the inside of the unit. Not difficult to do, but it takes some forethought. And then in most of those projects that we're seeing in New York right now, and not just New York, also here in Chicago, we see VRF systems, variable refrigerant flow systems for heating and cooling. So there is one component definitely that is being centralized and then distributed throughout all the different units via air handling units. The ventilator, if you have a centralized solution for your ventilator, you want that ventilator to be placed very closely to the exterior wall, which is a bit of a challenge because in multifamily projects, the exterior wall space is premium, but there are very small units available on the market, and with, again, smart design and thinking ahead, this is not a big issue. The ventilation ductwork should be kept separate though from the fan coil system of the VRF system, because both airflows are different. All right, and then there's also the solution to just treat every unit as just basically just like a single family home, and to basically decentralize everything. Every unit would get its own mini split. Every unit would get its own HRV, ERV, and distribution system. Final word on when we get into high rises and taller buildings. Again, here's what we recommend. Under our agreement with EPA and Zero Energy Ready Home, the apartments each have to be compartmentalized anyway. And the idea here is to essentially decouple each of them as if it was its own building, if you will. And through making these units airtight, we also neutralize the pressure plane. And if each apartment has its own ventilator, there's absolutely no stack effect issue here in this particular case. That is the ideal solution for indoor air quality and controls for the occupant. And then last lesson learned, very important lesson, certification is important. The third-party verified QAQC is absolutely critical for the performance of these projects. I've come to think of what we do as energy engineering. I don't know why I did not think of it that way right from the get-go, but the buildings are engineered to be tuned, and the systems are engineered to work with very small tolerances. So for one, during design, we need to make sure that we're hitting our targets and we're not just like hitting the numbers, and but the model is never checked, and we make a grave mistake, and then we undersize the systems potentially. And then step 2, during construction, we can do a phenomenal job during design and specify everything exactly and properly. Then if people switch out materials on site, if the air barrier is not tested multiple times up front, the team will not be able to get there, so on and so forth. So quality assurance is absolutely crucial, that all these important components that lead to a well-performing multifamily passive building are in place. As you likely know, under the PHIUS Plus certification program, the final certification is only awarded after the very thorough inspection from the on-site, from the infield, is coming back to the office, and the model is being updated with what was measured in the field for systems as well as for the envelope. And if the project then still meets the targets, that's when the plaque is awarded in the final certification. At that point, so we are at this point still not requiring any monitoring devices, but from experience we've seen it's really critical that you have some form of a feedback system, better than just having the whole building energy use over 1 year. Because if that energy use over 1 year is not matching what you had projected, you need more detailed information on where the energy is being consumed and where it might be off from what you had expected, and then you're actually going to be able to identify the problem. So very crucial. And what we've seen from our projects in the field, those that had more detailed dashboards and feedback systems, they were actually able to tune the building again after 1 year, and then match very closely what we had predicted. So one of those projects here is the Orchards at Orenco again. The kind of salmon-y line right here was the PHIUS Plus model, and the green line depicts what was actually measured in the project, and they match very well. We also modeled it in the under the PHI protocol here, as I said earlier, and that model was significantly over predicting what was actually then happening in the field once measured. And here you can see the PHIUS Plus model aligns very well with the measured. We over predicted by about 2%. The black bar on the left, you might want to ignore for now. This is just like as if the project had been modeled to ASHRAE standards, just as a comparison, like how much savings there is. But again, the savings for passive building performance is likely greater than what you're seeing here. We were not able to really validate the ASHRAE project because it was never built. It's very theoretical, just for reference in there. And then last but not least, really quick, couple exciting things for you, hopefully that gets the juices flowing. Buildings are getting bigger. Here in Chicago, we have been working with a developer on a 259 unit, almost all glass building, 20% spandrel, rest glass. And initially it was just, we were curious, could we do it? And the news was, yes, we could do it. And it was actually much easier than we had expected. The biggest upgrade was required for the windows. The walls, roof, ceiling, parking garage, slab and grate were the same as the developer's baseline. The air tightness was a big one. That got us there most of the way. So between air tightness and windows, we almost got the job done. But then, of course, also in large buildings, again, we need to take action to control the internal loads. And in this particular project, a big deal, halls and corridors, the lighting power density. If we can control that, that also gets us quite a ways there to meeting our targets. And then everything else had to be upgraded of the mechanical system in terms of efficiency. Of course, you can see the numbers here. ERV efficiency from 50 went to 85, cooling SEER from 13 to 17, so on and so forth. So some significant upgrade in the mechanical systems, but the reward is pretty awesome, really. We were able to reduce the energy consumption significantly from the baseline, and a little bit of renewable energy was required here to meet the source energy target. So good news for those who are trying to plan glass buildings and don't want to compromise and give up on them. You can take those designs to passive building standards as well. And again, different kind of depiction here in terms of reductions. It's super significant. So if we build glass buildings, we really need to make an effort to build them well. And if we do so, we can hit our global carbon reduction targets also with those building typologies. A couple details here from a team here in Chicago who's working on this, like from a detail from previous projects that they had that was not good, as you can see right here. And once they got done with their detailing, they were able to very quickly to improve the wall and to design very nice details that then actually allowed them to meet the targets. And last but not least, just quickly, a couple really cool projects that have been completed that are now occupied. That are going towards zero. And this is why I'm showing you these here. This is the Beach Green North project in New York City. Bluestone organization finished this project. It is now fully occupied. It has a PV system and combined heat and power that provides roughly 25 to 30% of the remaining energy that is still there in the passive building. It is not getting it all the way to zero, but it is a good way there. So very cool project right here. And then one in San Francisco in the Mission District here, recently certified. This project is a nanogrid. Basically one building a microgrid project that is still connected to the grid, but it produces enough energy and it overproduces to charge the cars in the garage and to keep the building comfortable, the condos. And the canopy that you see up there, that's where the PV panels live. They're very unobtrusive. It's a beautiful roof deck, really, really fantastic space to be in up there. Great project. So you can see that, and of course here the Rocky Mountain Institute that has been overproducing for a couple years now, just with the PV on the roof. So we're getting there. The envelopes are meeting PHIUS Plus standards, and then various levels of added photovoltaic combined heat and power, and is taking us to the path to zero. And with that, I like to end and maybe take a few questions. And I hope that you guys can join us for the next sessions on envelope detailing and mechanical systems.
Fantastic. Thanks, Kat. I do have a few questions for you. Question number one, is the 2 to 2.5 cost premium for PHIUS multifamily compared to another green building standard such as LEED or a code building? Does the cost analysis include the costs of QAQC?
I believe it does include QAQC, the added soft cost. And yes, it did. And it is compared to a basically code baseline. So for example, the Charm project in Maine, Portland, Maine, they had a fixed budget. They can only spend X amount of money on affordable projects. They can't go any higher. So they had to make it work within that budget. Yeah. So it's compared to the baseline that the affordable developer would be using otherwise.
All right. I have a question about WFI, please confirm that the surface area for air leakage is the surface of the model measured in WFI and not the exterior volume at the weather barrier.
I believe it is the same area that ResNet calculates. We're following ResNet protocol to calculate that. And I think, I don't want to say anything wrong. ResNet protocol is the rule.
Okay. With the use of lower R value windows, does the comfort offer remain the same? Aren't the surface temperatures going to be higher and lower, more than 7 degrees?
Yeah, so we are expanding that range a little bit. And there are a couple of reasons for it. For one, the air handling and space conditioning capacity that most units come with, we have more capacity in the units than we need, for one. So if there was a comfort issue, then we would have enough space conditioning to make up for it. But the way I understand it is really mostly the pooling of cold air on the floor of underneath of a window that is the problem here. And so when you have full height glazing rate, full height glass unit in your apartment, then you have to be more careful. Yes, but other than that, it seems to be okay to enlarge that 7-degree difference a bit for comfort. And Graham is actually working on that right now. We will have some comfort requirements that we will come out with that box the campus when folks are designing that, and we will require comfort checks, and we will give folks some design criteria for that.
Okay, so I've had a few questions about the slides and the recording. We recorded this event and we will share a link to that recording shortly. So please keep an eye out for that. It'll come via email in the next couple days. And our next question is, what happens to IAQ if power is lost for long periods?
Well, IAQ. So we always recommend that you design for natural ventilation. So if power is lost, open your window. It will cause some energy loss, but that's how you will be able to ventilate. Yeah, so there's a little bit more to it. So under PHIUS Plus 2015, we actually allowed natural ventilation to be counted into the energy balance. In 2018, under 2018, we no longer allow that knob for a reason, because it's unclear that people will open their windows. But that all said, you need to design for enough operable windows that you can open and ventilate naturally. Katrina, are you still there? Did I lose you? Uh-oh. Katrina, hello?
Hi, Kat. So sorry, I had muted myself and then sorry about that. Okay. Were the high-rise multifamily buildings analyzed for PHIUS Plus 2018 source energy target or the previous PHIUS Plus 2015?
The ones that I showed were previous PHIUS Plus 2015.
All right. I think that's all the questions we have right now.
Cool. Well, maybe we can make a quick plug for the conference in Boston in September 19 to 22. Would be great if you all could join us there. There will be much more on passive building, multifamily, commercial, mechanical systems. We're kicking into high gear here. It's going to be a fun conference.
Yes, it will. I am just going to show my screen for one quick second, and I've got your CPHC CEU self-reporting information displayed. Please take note of the URL phius.org/cphc/self-report. And our verification code today is 18529. And we'll take care of the AIA credits on your behalf. And we hope to see you all in Boston in September. Thank you, everyone.
Thank you.